Hello, so our lesson for 5.2 in Algebra 2 is going to discuss the analysis of different polynomial graphs, and we're going to be using a lot of technology today. So, not that though, let's get rid of that. We've been doing some pre-calc fun. In Algebra 2, it is not required that you have a graphing calculator. However, we're going to be using them quite a bit during the course over the next few months, frankly. And if you can get an emulator on your cell phone, that would be ideal, or on your computer or tablet. I know if you have an Android device, there's a free emulator called Wabbit, EMU, W-A-B-B-I-T, EMU for emulator. And it's going to look exactly like mine looks here on my computer. You can choose the color edition calculator like I utilize. Of course, you could just buy your own calculator, but we're going to be doing a lot of calculator work today. So, 5.2 is the section. Let's take a look at this first example. So 3x to the third minus 9x plus 1. Please pause the video and get this typed into your graphing utility. I'm going to do the same. Alright, so in our y equals menu, I have our function typed in. All of our plots are turned off. And then just so we're kind of looking at a standard window, I'm going to go back and hit zoom 6, which is our -10 to 10 window in both domain and range directions. And we have a cubic graph, and that is the shape that I would expect to see on a cubic polynomial. And I think I can see all the pertinent pieces. We're going to have to find them now. So, without understanding calculus, you're going to have to use some graphing utilities to help you answer the next few questions. So we're going to find our x-intercepts, any maximum bump, any minimum bump, and then we're going to find intervals for which the function is increasing versus decreasing. So let's start by finding all the intercepts, and I can estimate where the intercepts are, and I notice there are 3 of them. And they're not going to be at nice whole integers. I can tell from the way they're not lining up with the tick marks there. So to find x-intercepts, remember on your calculator, you go to your calc menu, and then you choose the 0 finders. There we go, enter. And then it doesn't matter which one you find first, second, and third. I always kind of go left or right. So I'm going to drag my cursor over so that it falls a little bit to the left of this first x-intercept. Now when I say drag, normally I would just hit the left arrow and pop over that way. But my emulator has a bit of a delay because of the computer speed. So I'm actually just going to type -2. It's going to make the cursor jump over to x equals -2 along the curve, which is to the left. And then notice when I hit enter, it switched the directions. Now it says right bound. So I need to drag my cursor so it's a little bit above the x-axis. So you guys will just be hitting your right arrow a few times like that. Enter. You could have done the jumping thing also. And then when it says guess, just make sure those 2 blue lines that showed up on your screen are kind of surrounding the x-intercept that you're trying to find, which they are. And we're going to need to jot this down. Let's go to the hundredths place. So -1 point, actually no, yeah, hundredths is good. -1.79. So, I need to jot that down before I forget. And there's quite a few examples on this lesson. And for the sake of time, because I have a class starting in about 10 minutes, I'm just going to do a few examples here. So one of the x-intercepts is at, what did we just say, -1.79, 0. And then we're going to find 2 more. So here we go. I know the y values are 0. That's not going to be a surprise. Alright, we're going to go through those steps again, and we're going to find these next 2 x-intercepts. So second trace, 0 finder, left bound. It's technically already to the left of it. I just don't like how far away it is, so I'm going to make it pop over here to where x equals -1. -1 is a little closer, but still left. Enter. And then right bound, I'm going to go with x equals 1. And then the guess is somewhere in between there, so yep. So we have another 0 at 0.11 if I round to the hundredths place. And one more. Second trace, 0 finder, which you can just type 2. Alright, left bound, I'm technically already left of it, but I'm going to go a little closer by hitting a 2. Ooh, that was a mistake. I have to pull that up again, because I can't count. I should have just gone to 1. My bad. Alright, try again. Alright, so left bound. Let's try 1, Abruzzo. That would be to the left of that x-intercept. Apparently 2 is to the right, but I'll go a little bigger and go 3. And then my guess is in between there, so yes, enter. 1.67, rounding to the hundredths place. Oops, wrong file. 1.67. This is usually where I ask the kids, what was it? Because I already forgot. 1.67. So on my graphing paper here, I'm going to plot an estimate for all these points that we just found. Negative 1.79 is not quite to negative 2, so do the best you can. This is just after the origin, and this is not quite to 2. Oh boy, that's going to be a really tight fit here. Alright, the maximum and minimum, they are not what we call the absolute maximum and minimum of the curve because it does have an infinite range because it's a cubic, but this is the maximum bump where it does reach kind of a peak, and then there's a minimum bump down here. So they're called relative max and mins, but these could still find them. So I'm going to find the maximum first. So I'm going to choose maximum finder, and then when it says left bound, right bound, I need to drag the cursor so it's a little bit to the left of the maximum bump. So I'm going to do that thing where I hop again. I'm going to go to negative 2. That is definitely to the left of it. And 0 is definitely to the right of it. And then guess, I'm just going to be somewhere around there. Alright, so the ordered pair, the negative 0.999 is a pixelation issue, so remember that really just means negative 1. So it's at the ordered pair negative 1.7. Hello, throwing my pen. So on my paper here, I have a max at negative, I already forgot what it was, negative 1.7. So on my paper, I'm going to plot negative 1.7. And then, for my minimum, same stuff, but this time you need to pull up the right command in this menu. We're finding a minimum this time. So choose number 3, the minimum finder. Left bound of this minimum, I'm going to go with 0, surely to the left. Right bound, I'm going to go with 2, and then my guess is in the middle, so it will find the correct minimum once I hit enter. And then we have the same pixelation issue here, but it's 1 comma negative 5 is our minimum. Oops, wrong one. 1 comma negative 5. Right in the right spot, Abuzo. If you didn't have, you know, prompts like we do here on the worksheet, you would have to label them as max and min on your paper, so just be aware of that. So 1, negative 5. Now this is where I'm going to have like a life failure, because I'm supposed to play connect the dots next, okay? I'll do this one just so you all can have a giggle at my terrible drawing. Oh, no, it's so bad. Alright. It's really unfortunate. Okay, so it was supposed to look like that, and this is what I came up with. So, not great. Let's go back to the computer screen here. I have the ability to do that because I'm your teacher and I have technology. Alright, so the next question is, when is your function increasing versus when is it decreasing? And what I'm asking you for, you might want to make a note of this in your notes. These are domain intervals. Okay? So when I ask you when is it increasing, I'm asking you to tell me along the domain, so just the x's, when is it going uphill? Like a roller coaster, that would be increasing. So you have to read starting from the left side and moving towards the right side, because that's how we read domain. If this was a roller coaster, this would be considered a going up the hill roller coaster, right? So this is an increasing curve right here. And then it gets to the top of the roller coaster, and then it starts decreasing, going downhill. And then it switches again at the bottom of the roller coaster, and it starts increasing again. And it increases forever. It's like the worst roller coaster ever. So if you could figure out where exactly it had what we call turning points in your domain, then you'll know when the interval starts and stops. And we found those. Remember the max and min? Those were the turning points of this curve. So the domain value at this maximum was negative 1, and the domain value at this minimum was positive 1. So when I ask you when is the function increasing first, increasing would be along this part of the domain and also this part of the domain. So what we say is, this is a little confusing, so hang with me, the increasing part of the curve technically starts like at negative infinity, doesn't it? Because it's increasing from the beginning of its domain. And then once it gets up to this point here, which was negative 1, it stops increasing. It's going to have a turning point. Now please put a parenthesis, because when you're at the top of the roller coaster, you're like flat. You're not increasing or decreasing. And then remember our friend the union symbol? We're going to use a union symbol here because there's another interval where the roller coaster was increasing, and it starts right here, which is at x equals 1, and then it keeps increasing for the rest of its domain, because it's going to keep going off to the right forever. Really slowly, but it will go off to the right forever. So that's the increasing interval. The decreasing interval is a little easier, because that was just the chunk, remember, right here in the middle of it. So it is decreasing from x equals negative 1 to x equals 1. And again, You can't use brackets here. Hello, -1 to 1. Because at -1 and 1 on the domain, that's that flat part of the roller coaster where they're not going anywhere. They're just at the top or the bottom of the curve. Okay. So for me, I think the increasing and decreasing interval is the hardest part for children. One more thing I want to talk about is the general domain and range of the curve, so an old concept here. The domain of that curve is a polynomial, so it has to be -infinity to infinity. That's a no-brainer. And then for range, how low and how high did it go? Remember, this was a cubic, so it went down forever and up forever. So it also has a range of -infinity to infinity. And then I have one more old topic for you. End behavior. I'm going to ask you about end behavior again. So the template is f of x approaches what as x's go to the left? And our f of x approaches what as your x's go to the right? So back up to my curve here. On the left side of my curve, it's going down. And on the right side, it's going up. So we have to remember how to say that in our fancy notation. So on the left side, it's going down, which is -infinity. And on the right side, it was going up, which is +infinity. And remember on the last time we tested end behavior, I probably gave you guys like a half-filled-in template, and you just had to fill in these blanks. This time, I'm not going to give you this part either. You have to know that one of the x's is -infinity, and one of the x's is +infinity for left and right. Okie dokie. I think I have time for one more. Let's get this guy typed in. I'm going to pause my video. You do the same and get it all typed. Okay, so we have our function typed in, -1/4 x to the 4th plus 2x squared. And I'm going to be in a standard window again, and if that doesn't work, I'll adjust it. But that's a quartic. It's like a weird W shape, and that's exactly what I expected to see. It's upside down because it's been reflected, that negative out in front of the function. So no surprises there. Let's go find our x-intercepts. X-intercepts are technically when the function crosses the x-axis. So what we're going to find is at this point right here, which is at 0, 0, the origin, that's technically not an x-intercept according to most textbooks because it doesn't cross through. We saw in the last lesson that when you have multiplicity of a solution, that it bounces off when it's got even multiplicity, and that's what happens here. So I don't mind if you call this an x-intercept at 0, but for sure you guys are going to need to find those two x-intercepts. So let's do that. Second trace, 0 finder, and then there's going to be a bit of symmetry on this curve. So I'm just going to find one of them, and then I'm going to use my thought about symmetry to find the other one. So left bound, let's go 1, 2, -3 would be to the left of that guy. Boom. -2 would be to the right of it. And then the guess is in the middle. -2.83 when I round. So that other one must be +2.83. So for x-intercepts, -2.83 comes 0, and +2.83 comes 0. And if you said 0, 0, I don't mind, but technically it's not an x-intercept. But it does bounce, so it's of note because we're going to have to graph it. So -2.83 is like roughly right there. 2.83 roughly right there. Alright, this one's not going to be any better when I go to graph it, guys. There is also some symmetry for our maxes and our mins. If I find this max, he's the reflection of it across that axis, so I can just kind of find the one max and then figure out the other one. So, maximum finder. Left bound of that maximum, I'm already there, so I'm going to hit enter. Right bound, let's go like -1, that would be to the right of it. And then a guess is in between. So -2, 4, which tells me if this is -2, 4, this guy must be +2, 4. And clearly this minimum bump is at 0, 0. We kind of already saw that from the intercept conversation we just got done with. So for maximum, you had two relative maxes at -2, 4 and +2, 4. Yeah. And then this dip right there, and then once again, a fabulous, oh, I should label that as a minimum. There's a minimum at 0, 0. So bad. Okay. You know, that wasn't as bad as I thought it would turn out. But. Alright, so now for the new stuff, the hard part, in my opinion. The increasing and decreasing part of this roller coaster. I'm going to go back to my computer calculator, because I think that helps. And I'm going to erase this part. So this would be a roller coaster going uphill, an increasing roller coaster. And then this is also uphill. So when it says, when is your function increasing, over what domain is it increasing? Well, it's increasing starting at negative infinity, and then it's going to stop increasing once it gets to this part of the domain, negative 2. But then it picks up again at 0 and continues increasing until it hits x equals 2. So the domain over which the function is increasing is from negative infinity to negative 2. Don't include it though, because it's not increasing at the turning point. And then it starts increasing again at x equals 0 to x equals 2. Decreasing, however, would be this section right here, and also this section right here. So for domain interval, for when it is decreasing, that's from negative 2 to 0. And picks up again at 2, and then it keeps decreasing for the rest of the domain. So 2 to infinity. It's very hard for kids to look at that picture and realize we're asking for a domain interval. Like whenever I say, when is the function doing something, I'm asking you for an x value, because time and x value, x-axis, those are all kind of the same in math. So I use the word when a lot, even though there's no time associated with this problem. Alright, for the sake of time, I'm going to have to kind of put a kibosh on this lesson. But, oh, you know why not? I have a whole other topic to talk about. Real quick, let's talk about this one. You're going to like this one. This one's already factored. That's awesome, right? So I can see the x-intercepts really clearly. This is going to have an x-intercept at 2, or 0 at 2. This one's going to produce an x-intercept at negative 1. And this one's going to produce an x-intercept at negative 3. So if I'm being asked to graph this, it's fine. I could at least get that plotted, right? So x-intercept at 2, x-intercept at negative 1, and x-intercept at negative 3. What we would do after that step is we would have to find the turning points with our calculator. Now, if it was like a matching question, I should be able to match it up without using my calculator because I know where the x-intercepts are and I know the general shape. This is a 1, 2, 3 cubic, so it's like a relative of this graph. I'm just not really sure where the maximum and minimums occur. So if I had more time, I would go through the act of plugging this into y1, typing it exactly like that, and then we would have to find the max and mins and plot them appropriately. All right? But we talked in an earlier lesson about the multiplicity. If you have even multiplicity, that means your function has a root that shows up twice for us for algebra 2, and it's going to bounce off of the x-axis. So it's not really an x-intercept as much as it's a location where it's going to bounce. So this guy has an x-intercept at 3, but since it has a multiplicity of 2, instead of crossing through, it's going to bounce off. And I'm not sure which direction yet. I need some more information. So over here, there's also an x-intercept, supposedly at negative 1, but it's got even multiplicity, so it's going to bounce again. So let me get this curve up here. Alright, so I said 3, negative 1. So again, you can use your graphing calculator to kind of help you with that part. However, if I look closely at it, it's a fourth power because it's x squared with another x squared, so it's like a W graph. And I don't know exactly what it looks like, but it's going to do something like this where it bounces off and then makes this W shape. I'm kind of making up the shape exactly. I would have to use a calculator to get some more information, but there you go. So the graph bounces off the x-axis at the points x equals negative 3 and x equals negative 1. Alright, so that's a good rundown of all the ideas. Again, I realize if you don't have a graphing calculator, it's going to be really difficult to practice this, so all the more reason to use your class time wisely. If you still need more time with the graphing calculator and you don't have one that you have access to or an emulator, that means you're going to have to come in and see me before and after school and during advisory, so I don't mind you coming in. I just feel like you have better things to do with your life. So get that emulator on your calculator. And that's actually the end of our polynomial unit. So our next unit's going to discuss exponential and logarithmic functions, and it's actually one of my favorite units, so take that for what it is. Good luck.